Hi everyone, welcome to this presentation. In this video, I'll be talking about some of the issues with recurrent neural net. Just to recollect, in the video series on recurrent neural nets for sequence data, we looked into the fundamental architectures of RNN and we understood the unique ability to process sequential information. We also covered the inner workings of RNN layer and describing how the information is actually processed over a time step and how the information is retained and updated over a sequence of time. We also saw some of the various configurations which are suitable for a specific NLP application, for example, classification or sentiment analysis. Um, Now the natural next step would be to understand how we can improve the recurrent neural nets and what's the need to improve or what's the need to improvise the RNN models. As the technology evolves, so does the demand for sophisticated architectures to handle complexities of the sequential data. And this essentially leads us to explore, advanced architectures like LSTM and GRUs. And in short, it's called long short-term memory and gated recurrent units. So these architectures actually address some of the limitations with the traditional, recurrent neural nets. For example, vanishing gradient problem and long-range dependency issues. So I'll be creating a new video series on LSTM and GRUs. And throughout that video series, we will dissect the internal workings of LSTM and GRU. We'll also do a meticulous, understanding of how each of the components in LSTM and GRUs work and how they address some of the shortcomings with the recurrent neural net. So some of the issues that affect recurrent nets, namely vanishing and exploding gradient. Vanishing gradient and exploding gradient, they are not just exclusive to sequence model. It is something which can affect any neural net. But sequence processing, since it is repeated over a period of time or period of time steps, the issue with the vanishing gradient and exploding gradients, it becomes really significant. And that can affect the performance or the model training of recurrent neural nets. We'll see how this is addressed by using the improvised architectures like LSTM and GRUs. One of the common requirement in NLP is long-term dependencies, and RNNs actually fall short in this specific area. And not that LSTMs and GRUs completely address this issue of long-term dependencies, but to some extent it does. So LSTM and GRUs kind of first step towards a better model for text data. So let's look at the vanishing gradient problem, why it typically happens. As you know, when you train a neural net, you initialize the weights matrix, and those weights are typically small, value. And when you multiply the weights over a, long period, or let's say a very long sequence, then the value of the weights become very insignificant. In that case, the gradient computed can be also negligibly small, and we say that the model is actually not learning. So that is actually a reason for vanishing gradient problem. So some of the reason why the vanishing gradient problem happens, one of the reason is the depth of the network. So, and sequence models are characterized by the requirement to have a very deep, processing, because you have a longer sequences, and you keep processing the input data or input text over a long sequence. Activation functions, for example, hyperbolic tangent and sigmoid functions, they can also be problematic and can cause the vanishing gradient problem to happen. So what are the ways to handle vanishing gradient problem? The use of activation functions in a judicious manner, and that's what LSTM and GRUs actually do. And I'll be describing that to you guys in the coming videos, how LSTM and GRUs actually utilize the sigmoid functions and tanish functions in their architectures. The other techniques are to initialize the weights, or find out more effective weight initialization techniques which can address the vanishing gradient problem. Batch normalization is another technique where you look at the activation values and you normalize the activation values for the layer, and that this also addresses the problem of vanishing gradient. Architectural changes, this is what we are going to be talking about, the LSTM and GRUs, and they have specific arrangements in their architecture which handle the vanishing gradient problem. Now, this long-term dependencies is a very, common problem, especially with the text data, where the sequence is very, very long, and standard RNNs typically suffer from, the ability or not having the ability to capture the long-term dependencies. So LSTM and GRUs can address that particular need. So let's take a look at some of the examples of long-term dependencies. For example, let's say the input paragraph is the economic downturn persisted throughout the year, and many businesses suffered, and leading to increased unemployment rates. So if you notice here, the unemployment has significant dependencies on economic downturn. But this economic downturn is appearing in the previous sentence. So this is a longer range dependencies, which can be problematic with standard RNN. Some more example here. Let's say for here the character evolution of a character in some novel, and that evolution or description of the evolution or the changes in the personality can be mentioned in various sentences. This is another example of long range or long term dependencies. So the solution to long term dependency or achieving the long term dependency is to use, at least as a beginning step, is to use LSTM or GRU's architectures. Gradient clipping is another method where if the gradient value is really, really becoming big, then in that case, we try to clip the values of the gradient. You can also try with the various different activation functions to contain the problem with the long-term dependencies. Limited parallelization. This is a problem with any sequence data. So with LSTM and GRUs, this problem will still be there. Although the architecture of LSTM and GRU sort of address the parallelization, and I'll be showing you how that parallelization is achieved in LSTM and GRUs. So the question is the parallel operation really possible, or can this be really achieved? The answer is actually no. I mean, for most of the sequence data, it is inherently sequential in nature. So by and large, this will be there. But if you choose advanced architectures like LSTM and GRUs, they are not purely sequential. By smart arrangement of the gating functions in LSTM and GRUs, certain amount of parallelism can be achieved. So some other methods apart from LSTM and GRUs is to use attention mechanism where we have need to focus on some specific words in the sequence. This also can be implemented in a parallel manner. So attention mechanism is very popular mechanism in the modern transformer architectures. In fact, the transformer architecture is designed to be parallel. So finally, in the sequence, journey, or the models for sequence processing, we will talk about transformer and the bird, and we'll see how things are processed in parallel. Yeah, another issue that we have in the standard RNN is lack of global context. Again, this is not exclusively a problem for RNN, even LSTM and even transformers and the modern day large language models, they also suffer from the global context. I mean, like we humans, when we learn some knowledge, there is always a context around it, and our ability to contextualize is really really big. Okay, but in case of neural nets like RNN, LSTM, transformer, and BERT, the contextualization or capacity to build a context is typically limited, like 4K or 1K. That kind of limitation is always there. So again, the answer is we will have to use some of the advanced architectures like transformer and BERT. LSTM and GRUs are like a stepping stone or first step into modern sequence modeling. They do address the need for global contextualization. So that's pretty much, these are three, four issues that we have in the, sequence data processing. And we'll see how these are addressed, at least partially, or in some cases, to 100% maybe. We in the architectures that I'll be covering in the next series of videos, LSTM and GRUs. Thank you. We'll see you in the coming videos on LSTM and GRUs.